Okay, so in this next video, we're going to explore a little bit of how these diagrams correspond to higher categorical geometry. So I've got loaded here is an example where now I have stuck some labels inside the boxes, and in addition to just the simple Opetopic diagram, I now have a little piece of geometry that I've drawn down here for you to start to get an idea of what's going on. So this diagram here, if you were diligent about it and thought about what you could get in very low dimensions, is, if you think about it, the only possible thing that you can get in dimension 1. The reason is the first set of boxes needs to be linearly nested, and the second one needs to be a single cell. And right, I guess I'll let you continue to think about that, but after a while you'll realize this is the only possibility. It will still, my little SVG file here is still going to highlight the things for us, and now I think you can see very quickly that the boxes correspond to cells in their particular dimension. So here we've highlighted X, and it highlights the little dot, which we think of as an object, a zero-dimensional cell, and Y over here, which is also a zero-dimensional cell. And you can see all the zero-dimensional information of this arrow here is contained in exactly those two cells. And F, on the other hand, records the connection between those cells. F is up here in the next dimension, in dimension 1, so that's why it's pictured in the picture there as an arrow, and it records the information that it has an input called X and an output called Y. So not a whole lot going on in dimension 1 here. Again, the only possible opetope of dimension 1 is exactly this one, the arrow, and this is what it looks like, and these are what its cells correspond to. So let's move on to dimension 2. In dimension 2, there are already infinitely many possible solutions. You can basically have any number of nested boxes in the first thing, and then you'll have a bunch of arrows with a single output, and finally a highest dimensional cell with the number of leaves is the number of arrows. But we have the same thing set up here. The zero-dimensional things will be highlighted by the little program here. Oops, and I'm getting a little rendering error there. I think that's Chrome, but maybe if I reload this, it'll go away. Anyway, so ignore the rendering error, but right. Again, the boxes here in dimension 0 are exactly the 3 zero-dimensional pieces of this two-dimensional cell. In dimension 1, we see exactly the one-dimensional pieces, so that corresponds to G and that corresponds to F. And then finally we have H down here. And then the top dimensional thing is a two-dimensional cell, and it corresponds to this 2 arrow. So this here is a picture of a simplex, and then this is the Opetopic diagram, which depicts that simplex. And finally, for a more complicated example, let's look at this one. Here we have a 3-dimensional opetope, and when you look at the diagram down here, you can see it's a sort of pasting diagram of 2-dimensional cells here on the left, and a single 2-dimensional cell here, which will serve as the output on the right. And this 3 cell in the middle is interpolating between those spaces. So in this picture, for example, H over here on the right is identified with H, on the left is identified with H here on the right. So you should picture sort of taking this whole picture and sliding it over on the top, and then bending it out of the screen, and imagine A is the 3-dimensional space that's sort of left in between when you do that. And the whole thing should really look kind of like a turtle shell, with this on the bottom and these things sort of curved out of the screen on the top, and A is the 3-dimensional space in between. So again, when you pass through the elements of this SVG file, it will highlight what they correspond to in the geometry below. So here are 4 zero-dimensional pieces of this cell, and they are exactly X, Y, Z, and W. And then over here we have the various one-dimensional pieces. Every cell of dimension 1 appears in this picture exactly once. Here are the two-dimensional pieces. So if I highlight a particular cell X, it's the two-dimensional space filling in that loop. Z is the two-dimensional space in that sort of curved twisted triangle there. S is the two-dimensional space connecting those three inputs. And finally, A is the three-dimensional space, as I mentioned before. Now, what's also going on in these pictures as opposed to in the last video is that when I highlight a particular, say, arrow, not only does it show me what line that corresponds to the next dimension higher, which is right over here for G, it also shows me the lower dimensional faces which comprise that cell. So you can see here it's highlighted exactly Y and Z, and in the picture you can see that Y and Z are exactly the input and output 0 cells of this one cell G. For a more interesting example, consider M down here. M has an input X and an output W, which you can see highlighted in the dimension below. And moreover, if you're curious how to read this off, the answer is that the faces in the next dimension down are exactly the lines which cross the boundary of this box. So M is this outer box here going around the outside, and you can see that a line crosses it exactly here on the top and here on the bottom. And if we read off in the picture, that's X up top and W on the bottom. So the picture, the diagram also records the input and output cells in any dimension. And so, for example, this line here in the middle, which corresponds to Z, does not touch the boundary of the box M, and therefore it is not one of the immediate faces of M. So the same reasoning applies here. For example, if we consider this 2-cell S, it has 3 inputs, 1, 2, 3, which are where these 3 lines touch the boundary, and 1 output down here going out of the bottom. And if you see both in the picture below and in the previous dimension, those inputs are F, K, and L, and the output is M, and those are exactly the cells highlighted down below. Right. So in these diagrams, they also encode, or the face structure of lower dimensions is encoded by incoming and outgoing edges, where edges come in from the top and go out by the bottom. So yeah, so you can again load up this picture in a browser and play around until you get the hang of which cells correspond to which pieces.